Hey folks, welcome back to the shrine of the hand-me-downs of the industry. Tonight we'll be talking about measurements, in particular measuring piston offset. We've got a couple pistons here from a Honda clone. Basically it's a Chinese clone of a Honda Cobb engine. The bore on this one is 54 millimeters, and is considered one of the newer engines that's out there. Basically you can see on any of the newer pistons that there's a marking for the inlet valve, and so it's important that when you assemble the piston you orient the piston properly. When you join the piston with the connecting rod, you can join it this way, you can turn it 180 and join it that way. Seemingly there is no difference. But if you not do it in a proper way, you can degrade the engine performance considerably. What the engine designers do these days is they're gonna offset the piston pin to one side. Typically it's being done to the inlet side. So wherever you have the inlet marking, that goes towards the inlet valve, and so this pin is being moved to that side. The distance is not much. It's typically less than 1 millimeter. So what we will end up with is that the wrist pin axis, so this is the wrist pin axis, you can imagine an imaginary axis that goes through there. It will not intersect the axis of the piston, which is here, so it's offset to one side, and that is the dimension that I'm trying to measure. I created a preliminary drawing for the piston, and all the other dimensions I already measured, and this is the only dimension that I have not measured that yet. I have a 0.5 millimeter offset here shown, but I'm not sure about it. This is based on the 3D scan data. We did a full 3D scan for the piston to establish especially these internal cast features. So a lot of these cast features are hard to measure with the calipers or any other ways. You know, it's easy to measure the outside dimensions, the machine dimensions, or the thickness of the groove, or this diameter, or this bore size. It's really easy to measure that with a caliper and other means. But getting to these nitty-gritty internal sizes and dimensions, figuring out if this is a cylinder, or it's a taper, or it's a cone, or whatever surface that is, that's why 3D scanning is great. So based on the 3D scan, there's an offset to the piston. I think it's around 0.5 millimeter, but I'm not sure about it, and that's what I'm trying to measure. Why do they do it? There is multiple reasons to offset the wrist pin. One of the reasons is there's a piston slap. When the piston is moving up and down, obviously when it's moving up it's going in one direction, and it's coming down it's going in another direction. So there's a moment at top dead center and bottom dead center where it's changing the directions. So that's when they say the acceleration goes to infinity. Obviously it's not infinity, it's some really high number, but that's when the piston slap happens, and that contributes to noise, and the designers are trying to minimize that noise. Another reason why they do the offset is to decrease the frictional losses. This is the piston goes up and down, it's got a lot of friction with the cylinder wall, and to decrease those losses they do the offset. And some of the designers say that the most important reason is to basically softening the reciprocating loading. The head of the connecting rod, the wrist pin, is offset relative to the center of the piston, so that the piston and the connecting rod not going to reach the top dead center in the same exact moment. and what it's going to lead to, it will spread out that impact loading at the top dead center and at the bottom dead center. And so I think that's the primary reason why they offset this pin. So here's my idea, how am I going to measure it. So I got this big plate. It's a rather heavy ground steel plate, and on the plate I installed the pin that is the wrist pin for that piston. And so I got it bolted down, and you can see that it's perpendicular this way, and it is perpendicular this way. Okay, so now if I set this down here and I put the piston on it like so, let me get you closer. Okay, so I put the piston on it. Out of the 6 degrees of freedom, I basically got rid of 5. Okay, so the piston is not moving in this direction, in this direction. It cannot rotate this way or this way. It can move up and down, but I can easily hold it down with some kind of bracket, some kind of mechanism. The only way the piston is turning is this way, okay, side to side. But I can prevent that by adding another piece parallel to it like so, and then using this angle bracket, and when I push the angle bracket relative to that, then it will align the piston. So now I know that the side of the piston, this side, is parallel to the edge of the plate. So now I can set this up on my mill and use basically the Bridgeport mill as a CMM and measure the piston offset. So let me set it up and I'll get you guys back. Okay, you can see the setup here. 1952 Bridgeport mill. I bolted the plate down to the table. Got this indicator, and the indicator is basically showing the run out, and you can see if I advance the table, it stays put. So the indicator is actually being held by the edge of the plate. So now I reset to 30. So if I go to the other direction, you can see that the needle stays put. So now I know that this edge right here is parallel with the travel of the table. So that's the X direction. Okay, so here is the second part of the setup. The first part is basically placing this plate on the mill table, and then I created this fence. Okay, this fence is parallel to the edge of the plate, which I indicated earlier. So this side, this back side of the fence, is parallel to the direction of travel. And what I did is I added this angle bracket. There's a little spring, and the spring is loading the angle bracket against the piston along the fence. So now I'm sure that to a certain accuracy, the bottom surfaces of the piston are perpendicular to the direction of X travel. Sorry about the noise, my phase converter is making the buzz. So the next thing I did is I installed a coaxial indicator. Okay, so I need to put down the camera, and I'm going to turn on the mill. And what you're going to see is that the mill is running, and the coaxial indicator is testing the internal bore of the piston. Now if I start moving the y-axis, you can see that the needle is going to stabilize. And if I move it more, the needle will go out of whack. So I'm going to go back and stabilize the needle and move the y-axis and move the x-axis until it completely stabilizes. And then once we're in that position, I can shut this off and I can go and zero out the x and y reading on my readout. So here's my readout, that's my y0 and x0. So now I know that the center of the spindle is coaxial with the center of the wrist pin. So the next thing I'm gonna do is put in an edge finder and then find this side edge and find the other side edge and basically do the measurements. So now I have the edge finder installed, and what I did is I lined up the edge finder to this top diameter on the piston. Okay, you can see that it's lined up and it's somewhat below that diameter, so where the edge finder would be touching the piston. So now I'm going to turn on the mill and use the edge finder to find that edge. Okay, so we're going to be coming in, and when it breaks off, that's when we know we found the edge. Okay, right there. So you can see that the edge finder broke off, and what we're going to do next is record this Y distance. So 28, 625. We're going to go and do the other side. Okay, so I set it up for the other side. What I'm going to do now is just use the edge finder to find that edge. Okay, so right there. Okay, so right there. So I found that edge. Now if you look at the display, you can see the reading is different. So 29.79. So we're gonna make a record of that. Okay, we are back. So I did some calculations, and this is what I come up with. Okay, so this is the piston here, and this is the piston axis. Okay, the intake valve socket was closer to our side, and that was the first dimension that I measured. So that dimension was 28.625, and then the edge finder that we used has a tenth of a radius to 2.54 millimeters, a tenth of an inch. Okay, so if we do the math, laid out, then the dimension comes out at 0.615. And then on the other side, we measure 29.79. And if we lay it out, the dimension comes out at 0.55. Okay, so 550 microns and 615 microns. So obviously the two dimensions, the two measurements are not equal, and that could be due to the, there's always measurement error. I mean, we are talking about 65 microns difference between the two measurements. So what I'm gonna do next is I'm gonna set up the other 5 pistons, and I'm gonna measure them the same way, create a table, and then basically just average it out and see where what the average is showing. So when I started measuring these parts, I looked at the piston again, and this was the number 1 that I first measured. You can see the intake is here, so piston was resting like that, and what you can see is that the coaxial indicator's tip left an imprint inside the bore, so I didn't want that to happen to the rest of the pistons. Right there you can see that groove. So this tip that I used on a coaxial indicator, you know, it's hard steel, this is soft aluminum, so it created that imprint, and I don't like that. So what I did is I went back and I installed you know, this different style of tip on a coaxial indicator, and basically indicating the pin, and it was a lot easier to go back to 0. And I want to show you, I need to turn it on, but in the same time I need to hold this with my hand. let me get you back. Okay, so we are back, and what I'm gonna do is turn on the mill. So what you can see is that the needle is basically going between 2 divisions. Let me zoom in, and you can see it clearly that the needle is bouncing between 2 divisions. Now, 1 division on this one is half a tau. So 1 tau is 2.5 microns. Half a tau would be basically 1 micron. So the runout right now is less than 1 micron. The other interesting thing is, if I zoom out, okay, you can see that the tip of the indicator is right at the top of the pin. Now if I start sweeping down, you know, I am moving down the quill, and you can see that the reading stays the same. So that gives me high confidence that this pin is not only at the center, but it is perpendicular to the plate. Okay, if it would be in an angle and I sweep down, then the reading of the indicator would be off. But you can see I can sweep up and down, and that reading doesn't really change. So what I'm going to do is use this setting and go ahead and measure the rest of the pistons. I went and measured all of the pistons, and these are the numbers that I came up with. And you can see they are pretty consistent: 2863, 65, 63, 65, and then these two, 5 and 6, are outliers: 28605 and 28610. And then on the other side, 29, 82, 78, 81, 77, 76, 82. So I'd say that this side is more consistent. So what I did next is I had some previous measurements where I measured this diameter. It's slightly different, so it's around 5340, but again I measured that just with calipers. Okay, so you can see this only has 2 digits. I don't have a micrometer that I would be able to use for 2 to 3 inches. That's what I would need here. So after I put everything into Excel and summed it up, this is what I came up with. So the average dimension for the piston offset came out to be 0.581. The minimum is 518, the maximum is 637, and so that will give me a range of 120 microns, where the symmetrical tolerance would be about 60 microns. So I am measuring 600 micron-ish dimension, and my tolerance is plus minus 60 microns, so that's 10%. So the tolerance field is about 20% of the size. Is that a good measurement? Well, heck no, I'm not proud of it. But considering everything, I think this is still a viable solution for a home tinkerer like me, you know, who doesn't have access to CMM. Obviously, you know, this offset, this piston offset, is not something that you can measure with a caliper. I mean, you cannot touch that axis and measure that axis relative to this axis. It's just not possible. I can assume that there are some similar measurements that I could have done. I was thinking about one where the piston would be vertical like this, and then I would come in and find the center of this cylinder, and then the pin would be installed in here, and then I would come in with the edge finder and basically touch the pin on one side, touch it on the other side, and that would give me you know, a similar measurement. The problem with that is that, again, the piston has another degree of freedom that I'm not going to be able to resolve, and namely this rotation. So when I want to make sure that the piston is perpendicular to one of the axes on the Bridgeport, you know, I cannot possibly set this up properly. Okay, so there will always be some kind of error. I can compensate for that error by bringing the edge finder close to the center. So that was one of my ideas. I went ahead with this solution. Kind of worked out fine. I'm just going to stick with this dimension for the time being. Here's a 3D model of the piston overlaid with the 3D scans. So the blue piece is the piston itself, the pink is one of the scans, and then the orange is the other scan. And you can see there's good agreement between the 3D model and the scan data. The round dots that you can see are the scan target stickers. So there are these round dots all over the place, and we place those for the scanner so that when we reposition the part, the scanner will be able to pick up where it left off earlier. In this assembly I also have the wrist pin installed. This scan captures the outside of the piston. You can see for high quality surfaces, if we have high quality surfaces, like in this case the wrist pin bore here overlaid with the mathematical model of the wrist pin, the software will not be able to distinguish between the two surfaces, so you end up with this zebra stripe pattern, and that's what we are after. That's when we know that the scan is high quality. So not many scanners can do that. Again, there's these targets everywhere for scanning, and you can see that the scan captured both the machine surfaces on the top of the piston and the cast surfaces with high accuracy. This is the inside of the piston, and you can see all the cast surfaces were captured with really nice accuracy. So here is the assembly again. If I turn on some of these sections, you can see that there's real good agreement between the scan and the 3D model. So right here you can see the contour of the scan relative to the 3D model. Here's another section where you can see that the mathematical model is precise, but the actual part is all over the place. If I match one side, the other side, which is supposed to be symmetric, will be off. But that's just telltales about the quality of the parts that we buy from China. Here are some more cross sections for the model, and you can see that again the agreement between the 3D model and the scan is really good. So there you have it. Piston offset measured in a 1952 Bridgeport milling machine turned into CMM. That's the way I do it, and I'm kind of proud of it. So thanks again for following me on this journey, and if you like it, give me a thumbs up, subscribe, come back next time. See you. Bye.